In this video, we will discuss various different definitions for acids and bases. When we talk about acids and bases, they can be categorized as acids and bases based on some properties. Acids are going to tend to be sour, while bases are going to tend to be bitter. So sour flavored things, maybe something like lemons or limes, that's going to be the result of acids present. Whereas something bitter, maybe like coffee grounds, those are going to be bases. Acids have the properties of dissolving metals. In a laboratory, we don't dump acids down the sink because they can dissolve metal pipes. Bases tend to be slippery. If you've ever spilled any sodium hydroxide on you in lab, which is not good, but if you have, it's kind of a soapy feeling. That's a characteristic property of bases. We detect acids and bases using litmus paper. Acids are going to turn blue litmus paper to red. Bases are going to turn red litmus paper to blue. Acids are going to be able to neutralize bases. Bases are going to be able to neutralize acids. Now, you would have gotten an introduction to acids and bases in your first semester chemistry class when you talked about neutralization. We've got some common acids and bases that you should know. You should know their names and their formulas. Now, the first definition of acids and bases we'll take a look at is the Arrhenius acid-base definition. According to the Arrhenius definition, an acid is going to be something that produces H plus in solution upon dissociation. So we put something in solution, it breaks apart, we produce H plus. So HCl breaks into H plus and Cl minus. HNO3 breaks into H plus and NO3 minus. Now, in both of these cases, notice that these are covalent compounds. They are molecules that happen to dissociate or ionize. So they're not composed of ions, but when they interact in water, we're going to get those ions produced. Now, the Arrhenius definition for a base is that a base produces hydroxide in solution. So sodium hydroxide would break into Na plus and OH minus. Notice that our Arrhenius bases, such as the sodium hydroxide, they are ionic compounds. They're typically going to be metal hydroxides. Ionic compounds that we put in water, they dissociate, and they have a hydroxide anion. Now, this definition implies that only aqueous solutions can be acids or bases because it's looking specifically at what happens in solution when something dissociates. But that's not the case. It's not just solutions that can be acids and bases. Now, one thing we also have to keep in mind is that H plus is highly reactive. It's a highly, highly reactive cation. The instant it gets released off of a compound, it's going to react with water in that solution. The H plus is going to interact with that water and it's going to produce what we call hydronium, H3O plus. This is always formed when we have an acid in solution. Acid dissociation in water can therefore be represented as follows. If I put my HCl into water, the H is going to come off, it's going to attach to the water molecule forming that H3O plus, and we're going to be left behind with that Cl minus. So that was our Arrhenius definition. We produce H plus, or technically hydronium in solution. If we are an acid, we produce hydroxide if we're a base. Now, our next definition is the Bronsted-Lowry definition. This category includes all of our Arrhenius acids. So anything that we describe as an Arrhenius acid is also a Bronsted-Lowry acid. But it's broader to include materials not classified as bases under the Arrhenius definition. So not all Arrhenius bases are Bronsted-Lowry bases. This definition focuses on proton transfer, so not just what's going on in solution, but specifically what happens to the hydrogen. Now, we're going to refer to an H plus as a proton. Remember that a hydrogen atom contains one proton and one electron. If one electron is removed to form H plus, then that particle is just left with a proton. So we call an H plus cation a proton. Now, according to the Bronsted-Lowry definition, acids are going to be defined as being proton donors. So they're going to release an H plus, giving it to water to form hydronium. Bases are going to be defined as being proton acceptors. They accept a hydrogen from water or from an acid. So we can look at an example of an acid, HCl. So we'd already saw HCl be the Arrhenius acid. The HCl dissociates, it releases H+. We also said that that H+ interacts with the water. Well, it's interacting through that proton transfer. The HCl transfers a hydrogen to the water molecule. And that's what's forming our hydronium here. So that's making HCl an acid. It is the proton donor. Meanwhile, the water accepts the hydrogen. It gains hydrogen, making the water a base. Now, when we talk about acid or base, initially we're talking about what we're putting into water. But we also can have, again, that water here behaving as a base because it can accept the hydrogen from that HCl. Now, if we look at our base example, here we've got NH3. NH3 is ammonia. We put that NH3 into water, and we're going to produce NH4+ and OH-. Here in this scenario, water transfers one of its hydrogen to the ammonia. So the ammonia gains hydrogen, making the ammonia the base. It's accepting the hydrogen, forming that NH4+. The water loses a hydrogen. It gives the hydrogen away to the NH3, making that water an acid. Now we've just looked at two examples and notice that in one case, water was a base, and in another case, water was an acid. It's really all going to depend on what water is interacting with. But water is one of those compounds that can behave as both an acid and a base. And when that's the case, we're going to describe that as being amphoteric. So water is amphoteric. In some scenarios, it can be an acid. In other scenarios, it can be a base. So in this chapter, we need to be able to identify acids and bases, whether it's Arrhenius or Bronsted-Lowry. So if we think back to our acid-base examples, from those equations, how can we tell if a proton has been transferred? So we can look at the HCl. So looking at this equation, how can we tell if a proton has been transferred or a hydrogen's been transferred? What we're going to do is we're going to see how hydrogen changes before and after our reaction. So if we're defining our acid as being the proton donor, it's got to lose hydrogens during that reaction. So our acid, so if we look at the HCl, it goes from HCl to Cl-. Here we have lost a hydrogen. We know we're losing hydrogen because our hydrogen count decreases, which means we are donating a hydrogen. So our acid will be the substance that decreases by one hydrogen during that process. So again, we're comparing the reactant side to the product side. We go from HCl to Cl-. We've lost a hydrogen, so that HCl had to have donated it. That makes the HCl the acid. Now, in identifying our base, remember we're defining our base as being a proton acceptor. So if we're accepting protons, our hydrogen will have to go up by one. So my base will be the substance that increases by one hydrogen during that exchange. So again, if we look at our HCl in water, producing the hydronium and the Cl-, my water starts with 2 hydrogens. It now ends with 3 hydrogens. The hydrogen amount has increased during that exchange. So the water has gained or accepted a hydrogen. Now, we said that things some things were going to cross both definitions. Anything that was Arrhenius acid is a Bronsted-Lowry acid because when that Arrhenius acid releases the H+, it transfers to the water, forming hydronium. Bases is where we're going to see some differences. Now, looking at ammonia, NH3, where acids are going to be classified as an Arrhenius base. So remember, the definition for Arrhenius base is that something produces hydroxide in solution. And we said earlier that if we put NH3 into water, that was going to produce NH4 plus and OH minus. We are producing hydroxide in solution. So we're producing OH minus in solution. That makes it an Arrhenius base. Now that hydroxide is being formed as a result of transferring a hydrogen, and so it's also going to be a Bronsted-Lowry base, so that ammonia falls into both categories. Now, my HCl we've already talked about. We said it's both an Arrhenius acid and a Bronsted-Lowry acid. The HCl produces H+. That's what classifies it as the Arrhenius acid. That H+ is donated to water, making it the Bronsted-Lowry acid. So we release an H+ that gets donated to water, classifying this as both an Arrhenius acid and a Bronsted-Lowry acid. Now, not all Arrhenius bases will be Bronsted-Lowry bases. Bronsted-Lowry bases will typically be Arrhenius bases, but not vice versa. And if we look at that, we said with our Arrhenius bases, many of them are going to be ionic, such as our sodium hydroxide. And if I take that sodium hydroxide and I put it into water, we're getting straightforward dissociation. I get Na plus breaking off, I get OH minus. That OH minus is not the result of proton transfer. It's just an ion that's present. And since there is no proton transfer, this is not a Bronsted-Lowry base. To be a Bronsted-Lowry base, something had to have gained a hydrogen. There is no hydrogen movement here. Now, when we looked at our NH3, we had our ammonia interacting with water. Notice that we used the double arrows. If we recall from previous chapters, we always use that double arrow when that process is reversible. And remember, if it's reversible, we're going to have something that has an equilibrium. Now, when we write equilibrium equations, we always write them in the direction we're interested in. So if we're interested in taking NH3 and dissolving it in water, we're going to write it to NH3 and water are the reactants. But we could write this in the reverse. And if we wrote it in the reverse, we would have NH4 plus OH minus, producing NH3 and H2O. In this scenario, to go from NH4 plus to NH3, my number of hydrogens goes down, which means that NH4 plus donates. So that NH4 plus is behaving as an acid. It gives a hydrogen away to reform the original NH3. At the same time, my OH goes from an OH minus to an H2O. Its hydrogen increases. So that means it accepts hydrogen. If it's accepting, then it is a base. Now, we've already identified that ammonia is a base and water can be an acid. It can take a hydrogen, or it can give a hydrogen to the ammonia. At the same time, those products can transfer hydrogen, reforming my original material. That's why it's a reversible reaction and will have an equilibrium. What this means is that in my solution, I have multiple acids and bases present, and this can have some impacts, as we'll see later on in this chapter.